This is Module 11, Lesson 4. It is your last lesson of the module. You're almost done with this one. What we're going to talk about this time is transformers. Transformers are another application of this whole electromagnetism thing, and something that you are surrounded by in many places in your life. You just may have never thought about it before. So here's the deal. When we generate power, and I say we, like when Duke Energy makes power, we have to turn the voltage up really, really high to get it transmitted up to like 100,000 volts. Now, if you know anything about your house, when it comes into your house, we have to turn it back down. We use 120 volts. A lot of other places in the world use 240. And I don't know if you've ever done any traveling, but if you use more than 120 volts on most of your appliances, it is not going to work out well for you. You have to have 120 volts or less going into the appliances that you use. Now, I'll give you a practical example of this. I lived in Russia for a little while, for almost a year, and when I first got there, I plugged my curling iron up into my little adapter set. Like you buy these little things that make your outlet cords fit into their outlets properly. I plugged it up, put it in the outlet, and I went to curl my hair like normal. And as soon as the curling iron touched my hair, it fried off everything that had touched the curling iron. Like I gave myself some really nice bangs. Didn't mean to, but I totally did. Now, what went wrong? I had 240 volts coming into my curling iron, which was meant to handle 120 here, and I forgot to plug up my transformer. So transformers are these little things that we use to either take our voltage down or to bring it back up. So basically, here's a picture. It was in the notes that I got this from. And the basic idea is you have your power plant, you've got your transmission lines, they've got substations, you got these high voltage transmission lines that you see that are way up off the ground, gets to another substation, and then it's sent out across the lines, and there's transformers all along the way. The transformers that are up on the poles, like this one right here, or sometimes they sit out at your house in like a big green box that's down on the ground. If you don't have power poles in your neighborhood or on your road, then you'll have these green boxes that have the transformers in them. The purpose of those transformers is to turn this voltage back down so that you don't fry your hair off or burn up your computer or your phone or your TV or anything else, because you only need 120 volts coming into your house. Now, some of the other transformers along the way, like at the substations, the purpose of the transformers there can be to turn the voltage back up because they need it to go up to be sent such long distances. You kind of lose it through transmission. So if we need to transmit a certain amount of power, you know already that P is equal to IV, and it says right here high voltage means low current. So if we need a set amount of power, and if the voltage is high, that means the current has to be very, very low. And power gets lost due to resistance, because there's resistance all along the way as it travels. That means that, if we can use a little bit of current, we lose the least amount of voltage possible. We need to send out huge amounts of voltage. So we use these transformer things. Well, basically, this is what I've already said. Transformers are used to convert voltage from high to low or low to high. And so what we do is we use electromagnetic induction to do this. Transformers have a primary and a secondary coil. You already know the term coil. You know the coil is like the loop of wire. We're going to use 2 loops of wire to make a transformer. We're just going to vary how many loops are in the primary and the secondary. And it says as the current flows through the primary coil, it makes a magnetic field. And then this magnetic field makes a current in the secondary coil. So here's some better pictures of this. This is a step-up transformer. So not paying attention to my words over here for a second, do you see the coils? We have the green coil on the primary side. So what we're saying is we're running electricity in through this coil. It's going to make a magnetic field. Now, transformers are usually wrapped around an iron core. If you've ever held on to the little the power packs, you know how like you have like a cord that plugs into something, and on the end of the cord you have this big box, and then it's got the prongs that go into the wall, if that makes any sense. And those little boxes can be heavy. They're really heavy. Inside that heavy little black box that plugs into the wall is a transformer. That core is what makes it so heavy. So when the green coil gets, electrified, it turns this core into a magnet, which makes electricity come out of the red side. Because notice, my red and green wires, they don't touch. I'm not just running electricity from one wire to the other. Now, how this works as a step-up transformer. First of all, a step-up transformer, it increases your electricity. It has more turns or more coils. More turns means, it says 20 turns versus 5. It has more wrappings of the wire on the secondary side than it does on the primary side. That means it's going to make more going out than is coming in. So whenever you have a transformer that increases your voltage, it is a step-up transformer. And I do have a little disclaimer up here for you that transformers generally only work when using alternating current. It doesn't work very well for direct because you would have to switch it on and off, and then you're just going to tear up the switch. Step-down transformers, they're just backwards from a step-up transformer. They have more primary turns or primary coils than they do in the secondary. That means you're going to have more voltage coming in than you do going out. Works by the same principle. Whatever comes in generates a magnetic field in the core, which makes electricity, if I can say it, an electric field in the red. So, what if we work with numbers with this? This is where you have to do some math. You need to be able to determine the voltage change with the transformer. Now, I gave you this particular formula, but my disclaimer is right here. They do not give this to you on the reference table. It is just a proportion. It is the voltage of the primary over the voltage of the secondary is equal to the number of primary coils, or the turns in the coil, over the number of turns in the secondary coil. Let's look at these for an example of how this works. In other words, if we have 50 turns on the primary and 10 turns on the secondary, you see what I just did there? We've got primary over secondary. I did the number of turns on that side. Then we can compare that to the voltage. It doesn't matter what side I put it on. Then, okay, what does that equal? That's a factor of 5, okay? In other words, the primary side is 5 times more than the secondary side. Well, does that work out over here? We have 1,000 going in and 200 volts coming out. Does that work coming out? Yep, it sure does. If we wanted to solve for one of these, let's say it didn't give us the 200, then I would just put an x in here and we could solve for x. And what we're going to get is 200. We could crisscross, we could cross multiply, and we'd have 50x is equal to 10 times 1,000. And when we solve for 50, we're going to get 200. So it's only necessary to work this out as just a simple ratio. Now, this equation you are given on your reference table, and it is used to determine the voltage or the power change. Now, why exactly, and I have my reference table here somewhere, why exactly it has the I in there in some ways, I will never know. I'm going to check to make sure that I wrote it right, because you would think that that's current. But it does have it on our papers. Let's see, it's at the very bottom. No, it is current. So I should have listed it that way. The primary current. I don't know what, I got carried away there with that. So this should be the primary current, and that would be in amps, and this is in amps. I think where I'm thinking power is because, well, like VI is power. So this is the primary power, and this does equal the secondary power. I think that's where my lack of thinking came from, was just to put that up there. But like, wait, what? This is our normal I that we've been dealing with. So unfortunately, I goofed. So it is used to determine voltage change. You could also use it to determine power change. You could also use it to determine current change. So What we're going to do with this one is know that they are multiplied. The voltage and the current of the primary is equal to the voltage and the current of the secondary, which does mean the primary power is equal to the secondary power. So let's see how these would work if we put them into some example problems. We have a step-up transformer. Automatically, as soon as I hear that, I automatically know, if I picture this in my mind, that I'm going to have more turns there than I am on this side because it's a step. No, just kidding. I'm so backwards. I shouldn't be making this many videos in a row, should I? So if we picture this again, if it's step up, I'm going to have few turns on this side, and we're going to have a lot of turns on the other side because it is a step-up transformer. We're stepping it up. It is converting 120 volts to 1.50 times 10 to the 4th volts. The primary coil has 24 turns. How many turns does the secondary coil have? Well, remember, we just simply need to set up a ratio. You need to put voltage to voltage and turns to turns. So we have 120 volts compared to 1.50 times 10 to the 4th. Okay, 24 turns, that's on top because that goes with the 120. And we want the number of turns on the bottom part of this. So how are we going to solve this? What we're going to do, you can hear my calculator as I get it out, is we are going to crisscross. We are going to have 120 times x is equal to 24 times, what is that? 1.50 times 10 to the 4th. So 24 times 1.5 to the 4th is 360,000. So that becomes 360,000. Divide both sides by 120, and we are going to get 3,000. The secondary side will have 3,000 turns of wire in order to get the voltage up that high. And that seems fair. That's a pretty high voltage. This is just simply going to be a ratio. Now, if you're curious, you could have flip-flopped these. I could have put the 24x on the left, and the 120 on the right. I could have actually put what was on the bottom on top. I should still get the same answer. Here's a second example. We have a step-up transformer with 1,000 turns of wire on the primary coil. I'm definitely not drawing 1,000 of those, so it's got 1,000 turns. And it's going to have a whole lot more on this side, 1 times 10 to the 5th turns on the secondary coil. If it's connected to a 120 volt power line, what is its step-up voltage? Well, this is the same one that we just did. Set up a ratio. We have 120 over something, because we've got voltage over voltage. And then we need to do the same way. If I put the primary side on top here, primary needs to go on top over here. We've got 1,000 over 1 times 10 to the 5th. How do we solve? Crisscross, cross multiply. 1,000 V is going to equal 120 times 10 to the 5th. That is not proper scientific notation, but it will work as far as getting in my calculator. 120 times 10 to the 5th divided by 1,000. I get 12,000 volts. Okay, we have 12,000 volts coming out of this on the secondary side. So does that make sense? Well, yeah, it's an increase of what? My mind is blank. It's an increase of 100. Well, to go from 1,000 to 1, 2, 3, 4, 5, that's also an increase of 100. So that makes sense. They both increase by 100. That's exactly what should happen then. Here's another one. We have a step-down transformer. So here is my transformer. It's a step-down. So we have a reduction in voltage from 120 to 12. So we're going from 120 volts to 12 volts. The primary coil has 500 turns. And I'm going to write this as a decimal point, 0.0300 amps. I have two questions. First of all, what is the power delivered to the secondary coil? Well, remember that we can find power by doing P is equal to IV. So that's my goal here. I need P is equal to IV of all the secondary stuff. Well, one of the ways that we could do this, remember, is we have our formula where we could do the primary voltage and current times the secondary voltage and current. Because if I look at this for a second, I have enough of these pieces. I have the voltage is 120, and the current on that side is 0.0300 amps. The current on this other side is what we're wanting to find, and then the voltage is 12. Okay, so let's see what we get out of that. Let's solve for I. Incidentally, as I solve for this, I'm finding the answer down here for that one. So as I solve for this, I should get, let's see, 0.03 times 120, and that is going to be divided by 12. So I get that I have a current right there of 0.3 amps, which is small, but it's bigger than this one. And then if I put it back together right there, for the P is equal to IV, I have 0.3 times 12, which is, of course, 3.6. So there's 3.6 watts of power on the secondary side. And we just answered our question down here that the current on the secondary coil is 0.3 amps. So there you have it. It is now time for you to do your first practice sheet for this whole module. You have some transformer questions working with all of these formulas just to make sure that you understand what you're doing. If you need help, please don't hesitate to let me know.